Okay, so now what we're going to do is we're going to kind of formally talk about the stuff that you guys did with those little cards, which was kind of like a play with it and see what you can kind of come up with. So now we're going to officially come up with names for different kinds of reactions based on the reactants that we see. So first one, we're going to talk about something called synthesis. And if you think about the name synthesis, it sounds like something's coming together. And that's what it is. It's two smaller things come together to make only one thing. Okay, and so a lot of those examples that you guys had were things like that. I have two magnesium atoms come together with one oxygen molecule to make two magnesium oxides. Now keep in mind, that and that are just there to balance. What makes this a synthesis reaction is I have an element plus another element coming together to make one thing. In this case, it's a compound. Keep in mind, these little letters here are just referring to it's a solid, a gas, and a solid. So really what we're looking at is we're really just looking at the formulas of what we have. The numbers of capital letters, if you even want to call it that. One magnesium has one capital letter, oxygen one capital letter, boom, two of them makes it a compound. Okay, doesn't have to be simple like that. Doesn't have to be an element plus an element. It can be two smaller things. Water and carbon dioxide can come together to make carbonic acid. But basically the idea is you have two smaller things making one bigger thing. Okay, that's a synthesis reaction. Decomposition is the exact opposite of that. And if you think about biology, you think of decomposition, decomposing leaves, compost, things like that. Things breaking down. And that's what decomposition is. Decomposition is things breaking down. You have one big thing breaking apart into two or more small things. And again, it's a compound, generally, breaking apart into an element and an element. And often it is the exact reverse of what you saw with synthesis. So, for example, water would break apart into the two elements that it's made out of, hydrogen and oxygen. Now notice the subscripts here. Okay, we'll talk about that later, but I want to just point out that these are diatomic elements, hydrogen and oxygen. And we talked about those in the past. Just mentioning it again, okay, that's the way they come. Now here's another example. Carbonic acid, this is what makes soda fizz. When it fizzes, or when it goes flat, it breaks apart into water and carbon dioxide, and that's why you see the bubbles in carbonic acid, soda, things like that. So combustion reactions are a little bit different. They're kind of like their own little weird category. And combustion, if you think about that, that means burning. So we have to have a fuel, and we have to have oxygen. Things don't burn without oxygen. You can have all the gasoline in the world, and if there is no oxygen, it's not going to burn. It's got to have something to produce oxygen. So the way the reaction is typically thought of is a hydrocarbon reacts with oxygen. So again, like I said, you have to have oxygen and you have to have fuel. And the products are CO2 and water. Doesn't mean that every time you see CO2 and water as a product, it's combustion. What it means is that that is the product of combustion reactions. But what we're really looking for is we're looking for these things called the hydrocarbons. And hydrocarbons contain carbon with some subscript. It could be one. Hydrogen with some subscript. It's usually not one. Oxygen with some subscript. So it's got all these are organic compounds is what they're called. And hydrocarbons have a lot of ability to make new bonds. And when those bonds are broken, they produce energy. And so it's a hydrocarbon plus oxygen forms carbon dioxide and water. So I'm just going to give you some examples. This is, gosh, I don't even know what kind of alcohol that is, but it's an alcohol. And again, carbon, hydrogen, and oxygen. Even though there's a hydrogen at the end, it still counts as a hydrocarbon. Plus oxygen makes CO2 and water. And it doesn't have to be written this way. It could be written O2 plus C2H3OH. Hydrocarbon and oxygen. Doesn't have to be written in the right order. This is propane. This is what's in your gas grill. It reacts with oxygen to form CO2 and water. Notice it doesn't have any oxygens in it. Okay, so in this case, the Z would have a subscript of 0, meaning there are no oxygens in it. Whereas it's all carbons and hydrogens. All right, single replacement. This is an easy one to get mixed up with regards to combustion because they have a lot of similarities. In a single replacement, you have an element and a compound come together. So one capital letter, two or more capital letters. That's what you're looking at. And they form a new compound and a new element. And the rule is the element, so the one that's all by itself, this guy, replaces the ion of like charge. And we'll talk about that more later. The positive replaces a positive, or the negative replaces a negative. So this is kind of the general form. A being the element plus a compound makes a new compound and a new element. So for example, here's my element, aluminum. Here's my compound, two or more capital letters. The Al and the Cu trade places. The Al now is part of the compound, and the Cu is all by itself. Okay, we'll talk about where the numbers come from. Again, solid, aqueous, aqueous, solid. That's not really so important as it is to recognize element and a compound. Or it could have been written a compound and an element. So it could have been written CuCl2 plus Al. The order in which they're written on the left side or on the right side doesn't matter. You have to recognize it as being element and a compound. Here's another example. This is an element, one capital letter. This is a compound, two or more. And in this case, the fluorine is replacing the chlorine because they both get a negative charge. So the K ends up with the fluorine and the Cl ends up on its own. Okay, double replacement, there's two different versions of this. They are when you have two compounds react. The way it works is that the positive ion, the thing written first, they trade places. That's why they call it double replacement. Both of them trade places with each other. And so what you end up getting is something like this, where A and C, A goes here and C goes there. So an example of that is barium chloride. And again, it's a compound, two capital letters, three capital letters. The Ba and the Na trade places. So the Na is going to end up with the Cl and the Ba is going to end up with the SO4. And that's where you get it. New compounds. This one is a special example of it. It's actually called an acid-base reaction. It's kind of a special version of a double replacement. I have a compound and a compound, but this compound has a hydrogen on it. That makes it an acid. And OH makes this a base. So this is technically an acid-base reaction, not a double replacement specifically. So this one, I want to show you this one. Lead and H, this is an acid, but this is not a base. Bases have to have OH on them. They're going to trade places. So you get PbCl2 and acetic acid. So this is an acid-base reaction. It's a special version of a double replacement. So there's two types. There's a precipitation one, and that one produces a solid. The reactants are going to be always aqueous. I mean, in a double replacement reaction, whether it's acid-base or not, it will be. One of the products is still aqueous, but the other one is a solid. And what you have to do is we have to use something called the solubility rules, and we will get to that. Then there's this acid-base, and I showed you the example on the previous slide. It's a form of double replacement reaction, but it gets its own category. And when you have an acid react with a base, it produces water. Okay, so that's a special example of a double replacement. You have an H in front, makes it an acid. You have an OH at the end, makes it a base. That's where you get your double replacement. Technically, the B and the H are double replacing each other, but when you put HOH together, you get water. That makes this acid base. So what we're going to do is we're going to go through, and I'm going to put these up here. You guys should have these in your notes. Now, all you want to do, what is it doing so long here? Come on. Is you want to look at them and identify whether you're starting with an element, a compound, two elements, two compounds, element and a compound, depending on what you're starting with. But you're looking at the capital letters. So I'm looking at this and I see element plus another element. That means this is turning into only one compound. That makes this synthesis. Okay, now I'm looking at this one and I see a whole bunch of capital letters. That's a compound. This, only one capital letter. That's an element. And it's not a combustion reaction because I don't see any oxygen. So this is a single replacement. Here I have something with carbon and hydrogen in it and oxygen. So this is one of my hydrocarbons, and oxygen makes this combustion. This one I have a compound and a compound. That makes it double replacement. This one is also a compound and a compound. So technically you could call it double replacement. However, it's an OH and an H. Makes it technically acid-base. And that would be the better answer. Initially, I'm probably going to let either one of them slide. But I will tell you that once you guys get good at this and you start to recognize it, I'm going to expect to see acid-base. And then here, all I have is a compound. That means all by itself. This is decomposition. So, quick summary, element and element is synthesis. A compound all by itself is decomposition. An element in a compound is single replacement, keeping in mind that if you have this element and this kind of a compound, it's called combustion. And then acid has an H in front, OH at the end is acid-base. Oh, wait a minute, what happened? I didn't see, oh, there it is, double replacement. Compound and compound. Okay, so this is how you can identify, and that's going to be really, really important because we're going to start to do stuff where you have to predict the products based on being able to identify the type, and this will tell you how to figure out the products, and that's what we're going to spend this whole chapter on. And this is actually, it's not super easy, just so you know.